We'd like to know whether a gaming investor should become a new partner in this casino. He's only going to do it if his conditions are met, and it appears that his conditions are, well, it has to be successful. And he considers the industry to be successful when the revenues for card rooms are above $1 million or when revenues for lotteries are above $20 billion. Okay, so notice that we have this condition. So when total gross revenues for card rooms are above $1 million or when gross revenues for lotteries are above $20 billion. Okay, so either one of those two conditions has to take place. Well, let's state that out. So the probability that the conditions are met. Okay, well, we can state that generically because that's what we're trying to find. Well, when are his conditions met? When either this happens, or even better yet, when both of those things would happen. So let's call this event right here, we'll just abbreviate that event CR for card rooms, and then we'll abbreviate this second possible event here, we'll just go ahead and call that L for lotteries. Okay, so we really want to know the probability of CR or L. Okay, well, what does that mean? Well, since we have an OR probability, based on our knowledge, that's the probability that card rooms are successful, plus the probability that lotteries are successful, minus the probability of card rooms and lotteries. Okay, so, well, we've got to figure out what information we have here. So he found that 50% of the time both sectors have been successful. Okay, so we know that the probability that card rooms and lotteries being successful, that occurs 50% of the time. So that's 0.5. And that 0% of the time, only card tables were successful. And lotteries were not. So the probability that card rooms successful and lotteries not successful, so I'll abbreviate this as not lotteries, is equal to 0%. Or, excuse me, I guess I should just put 0. Don't want to work in percentages and decimals, so I'll just write 0. We also know that lotteries were unsuccessful 30% of the time. So the probability that lotteries are unsuccessful equals 0.3. Well, obviously, we're getting into too many details here, and so far we can't unravel any of the bits and pieces of this here, other than we know that the probability of CR and L, which was something that we need, is equal to 0.5. Okay, so let's draw a little table to help us kind of identify the other pieces. So we know that we have card rooms are successful or card rooms are not successful. We know that lotteries are successful or that lotteries are not successful. Now, the reason we can partition these, it's like saying a person is either wearing a gray shirt or is not wearing a gray shirt. Well, that totally divides the entire population because either they are or they aren't. So now let's fill in some of the details here. We know that the probability that the card rooms and lotteries are successful is equal to 0.5. Well, that's card rooms and lotteries, and we know that that's 0.5. We know that the probability that card rooms are successful and lotteries are not successful, so card rooms successful, lotteries not successful, is 0. And then we're also told the probability that lotteries are not successful is 0.3. So that doesn't say anything about card rooms, that just says the probability that lotteries are not successful is 0.3. Alright, well, we know all these probabilities have to add up to 1. That is, all these situations have to establish the entire possibility space. And so now we can kind of go about seeing what we can figure out. Well, I'm going to do this in a different color just so we can keep in mind what we're calculating, what was given to us. So I will do this in, how about green? And we know that the sum of this guy and this guy has to equal 0.3, so this guy has to be 0.3 right here. It's 0.3 plus 0 is 0.3, so this is a total. Okay, well, we also know that this has to add up to 1. So far what we have here is 0.5, 0.3, and 0. Well, because this also has to add up to 1, probability of lottery being successful or not being successful, we know that the probability that the lottery is successful then, on the opposite end, has to be 0.7. So that alone helps establish that this must be 0.2, since 0.5 plus 0.2 is 0.7. Okay, well, notice that again, all these four numbers do add up to 1, and these two numbers add up to 0.7, these two numbers add up to 0.3, and now we can actually fill in extra details here. So the probability that card rooms are successful is 0.5. The probability that card rooms are not successful then has to be, well, the other 50% of the time. So we got a lot of details here, and now we can go ahead and hunt for what we need. So I'm going to transition back to a black marker. And so we're going to say, well, this guy right here equals the probability that card rooms are successful, which overall is 50% of the time, regardless of the state of lottery, plus the probability that lotteries are successful. Well, they're successful 70% of the time, minus the probability that they're both successful, which is 0.5. All right, well, that means 0.5 plus 0.7 minus 0.5 is just going to be 0.7. And so our answer would be 70% of the time. Alternatively, based on the definition of what OR means, it means card rooms are successful, lotteries are successful, or they're both successful. So technically, we could just go ahead and look at the three cells where that happens. So here is a space where card rooms are successful by themselves. Here's the space where lotteries are successful by themselves. And then here's a space where they're both successful. So really, we're just adding up these three cells here, which is the same thing that we get if we added this row plus this column. And because we're double counting this 0.5, notice that here we're subtracting it away. So our answer is 70% of the time the probability that his conditions will be met is 70%, which is fairly high, and depending on your professional opinion, you may or may not think that's a good idea.